We are about halfway through this week's lecture, and we definitely want to finish off the first refinements for the bridge controller. There are two more important topics I would like to cover. One will be about the so-called Livelock or divergence, will be the current topic, and the next one will be about relative deadlock freedom. We spoke about deadlock freedom in the initial model, but we want to see what deadlock freedom can really be proved as absent in the case of the refinement. That's something we'd like to talk about as well, but one thing at a time. Let's talk about the Livelock or divergence. And what I would like you to consider would be this particular variance of the initial first refinement model M1. Right? Let me just tell you what it is over here, and then I got some initial exercises for you, and also some stuff for you to think about first before we actually move on to illustrate what a deadlock, what a Livelock is. This example over here is a little bit contrived, a little bit artificial, but I thought it might be nice to really just at least show you some concrete example, like how Livelock can really occur, as opposed to just going over some bullet points. Let's see how that works, right? Okay, and so there will be two things that will be shocked about this particular variance of our M1. One thing is about it can be proved correct, actually, as far as the invariance is concerned. That's the shocking facts number one. And shocking facts number two will be about divergence, which I'll speak about a little bit later. Let's talk about shocking facts number one. If you look at this variance for M1 over here, let me show you. Let me just mention quickly about what the difference is compared with the original M1. So if you look at the invariance over here, we don't have the invariant number 4 and invariant number 5 anymore, meaning that we don't have the connection in invariant number 4 to say a plus b plus c equals n. I simply got rid of it, right? That's number 4. And remember, number 5 is about a safety constraint to say a equals 0 or c equals 0, right? I simply got rid of these two, right? So that's the new invariance over here, updated invariance, just for illustration. And for the new events IL in and IL out over here, I also got rid of their guards, so they're guardless. And if you remember what we discussed before, whenever you got any events, except for the init events should be the only event that you don't really have any guards. Other than that, any event that actually got no guards, meaning that it's enabled always, that should be like a warning sign. It should be a no-no in terms of the design for the events. That's something you want to keep in mind. Right? Let's say this is a variant of M1 that we are talking about. Shocking facts number 1, right? So let me just go over the bullet point for the exercises, and I will put some annotation. Right? Concrete invariants over here, invariant 1, 2, and 3, they are only specifying about the typing constraint for A, B, and C, right? Just saying A, B, C are simply just integers. I even changed the type from natural number into integer, right? Just so that I can demonstrate the Livelock later. Right? Anyway, so it's simply integers. They are simply typing constraint and nothing else. We have no connection to the abstract variable as the original invariant number 4 does, and also we have no addressing about the safety constraint of the bridge being one way as the original invariant number 5 does, right? We actually got rid of those. And this will be some exercise for you, right? You definitely can use this variant model as given, and you can try to generate all the sequence related to invariant preservation. I would say focus more on, well, actually we got only 3 variants over here, right? I think they are rather simple to actually try to generate and also to prove or unprove. I would say try to do this exercise over here about invariant preservation and also about guard strengthening. In some way, guard strengthening here is interesting because IL in and also IL out, they simply have no guards, meaning that their guards are simply equivalent to true. In that case, will you be able to actually prove that the concrete guards implies the abstract guard? Right? That's something we said before, right? So I would like you to do this exercise over here. Let me tell you the conclusion first, but you definitely should know how to prove it or how to disprove it. Okay? Let me tell you the conclusion right away. Shocking facts number 1. This particular variance model over here, shockingly, this model can be proved correct with respect to invariance preservation. And I want you to recall something I mentioned before. We said that correctness of your model is really relative. meaning that it depends on what kind of invariance you actually specify in your model, right? So as far as the invariants that are specified over here are concerned, they are to do with the types. That means as long as your events over here can really maintain the facts that A, B, and C are simply just integer, there is no connection to the abstract variables, and there's no addressing about the one-way breach. In that case, we can easily prove that the invariants over here are simply maintained and can be established. That means we can conclude our model is actually correct as far as these invariants are concerned, right? That's shocking facts number one, right? So you might be wondering, well, if we have such a crappy model over here, why can it be considered as correct? So again, you really want to understand. In the first place, you have to make sure the invariants should really capture as many constraints as possible. And if they only cover the typing constraint, it's a warning sign. It should also cover some connection with the abstract states, and also you should really capture whatever safety constraint you might be concerned about. If they are absent, in that case, even if you can actually prove correctness with respect to this particular model, it's really useless. Right? Let me write it down. It's a very important reflection about what we have done so far. You should not really assume you will always just be given the invariants that are complete. You yourself will actually have to come up with the invariants given the problem description. Right? That's really the point. Let me highlight this one over here. This invariant over here, in some way, it's incomplete. Because lacking two things. Number one, the connection to abstract states. And number two, if I can just maybe move this one here a little bit down, right? Over here. And number two, safety constraint. In this case, for our model number one, the refinement model, we should really say the breach should be one way, but there's no mention of the breach being one way in this variance of the invariance over here, right? Safety constraint, right? Safety constraint. They are simply just lacking. Okay, connection to abstract states and also safety constraint, right? These two are simply lacking. Okay, so proof correct over here is really relative to something that's actually incomplete. So whenever you declare that your model is actually correct, the follow-up question would be, what kind of invariance did you prove the correctness with respect to? In that case, if the invariant itself to be proved against is simply incomplete, in that case, even though you can draw the conclusion that your model is actually provably correct with respect to the invariance, it's not very useful. So that's why you have to make sure always reflect on yourself whether or not your invariance is complete. How do you judge? You want to make sure at least you try to address as much as possible these 2 points over here. One is about connection to the abstract states, the other one is about safety constraints over here. All right, let me just highlight it once more. So this is so important over here to remember. That's something we didn't quite mention before. Before you were given the completed invariance to begin with, but now I'm just trying to give you some alternative model in which case the invariant is not complete. In that case, you definitely want to make sure you understand, even though you could prove you can discharge the sequence about invariant preservation and establishment, but given that the invariant itself is actually incomplete, so the conclusion over here is provably correct, it's not that useful. Alright, so that's about shocking facts number 1 about this model. Let's now talk about shocking facts number 2, which is about these 2 events for which I took out their guards. Let's see how bad it could be. Let me start with some concrete transitions to start with, just to illustrate. Okay, let's say this. So we talk about concrete transitions. Right, let me put it a little bit lower over here. I will also put the abstract counterpart. Remember, somehow every concrete transition should be simulated by some abstract transition. I will do that as well. Right, so let me just put it here. Okay, that should be good. Let's say the following. Let me say inits, right, to initialize the system. Under what circumstances can these two events, the new events, occur? Well, apparently it should be always. They're always enabled because there's simply no guards, which are equivalent to having true as the guard condition. On the other hand, you can see for ML out and ML in, they still have their ordinary guards over here, meaning that they are not always enabled. They are only enabled when these two variables, when these conditions actually are evaluated true, right? But let's now focus more on these two events, especially because they are new events. The reason that we want to look at these two specifically is because those are the events that do not have, strictly speaking, the abstract counterpart. That's why we got to use the skip events to really simulate, right? So these two over here emphasize they are the new events, which does not exist in M0, right? Let's now talk about one particular system trace. If we can show some problematic scenario as a trace for our model over here, that means the model is problematic, right? We're showing some counter example. Pretty much like before, if we want to show that our model is not exactly correct, we can show some system trace, which will demonstrate some states violating the invariance that we specify, right? Similar idea. So let's now specify some problematic trace, which will go as follows. After the initialization, since we know IL in, IL out can always occur, what about we do this? So let's say IL in can occur, also followed by IL out, and then followed by IL in, and then followed by IL out. Is this trace so far possible? Let's not worry too much about how the variable values are being changed. All we focus on will be whether or not this particular trace is actually possible for the system execution as an abstract state machine. The answer is yes, because these two events are completely unguarded, meaning that it is always possible, it is possible to have a particular system run where we simply got IL in, IL out, IL in, IL out. They simply interleave with each other indefinitely without ever allowing the actual ML out and ML in to occur. Right? So far, so good. All right. It's really important so this will simply go indefinitely. All right. So it's really important to see that this will simply continue indefinitely, preventing other old events. When I say old events, I really meant these two, right? So you can think about these two are so-called old events because they already exist in the model M0, right? The old events. Okay, actually it's a different red. Let me just fix that very quickly. Right, the old events. And why is this particular trace so bad? Right? This is actually so-called a scenario where the two events diverge. That's something you will also see on the slide, but let me also mention the term over here. This pattern over here really shows this indefinite, this like an infinitely long trace. Actually, you can think about every system trace for the reactive system should be infinite because the system never terminates, presumably, right? So in this case, we really say that the new events diverge. Meaning that they simply just occur always without allowing other events to actually occur, right? That's really what diverge mean in this context over here, right? The new events simply diverge. Why is that bad? It may not be so easy for you to see at the concrete level. Let's talk about what will be the corresponding abstract scenario, right? You want to make sure whenever your refinement model behaves, it better be somehow consistent with how it behaves at the abstract level, which will be easier to see. At the concrete level, there might be too many details that you have to focus on, but if you can somehow reduce it to its corresponding abstract level, it will be much easier to see what the problem might be. Let's see that, right? And the only thing I want to add to this context will be, if you think about the corresponding abstract transitions. So we got abstract transitions. Over here, we know for the inits, it has the corresponding inits. This part is good. And for all the new events over here, ILN and also ILOut, we already proved actually earlier they actually is simulated by the skip events. Remember the skip, pretty much like a dummy events. So ILN over here really correspond to the skip over here. ILL over here also correspond to another skip, and this one over here also correspond to skip, and this one over here also correspond to skip, and etc. indefinitely. So you really want to think about at a concrete level, when you actually have this particular indefinite trace where there is simply no room for the old events to actually to actually occur, because the two new events actually diverge. It simply corresponds to the following abstract scenario, which will be this trace over here, which means after we initialize the system, we simply skip. Number one, this scenario here is not really deadlock, right? Number one, it's really important to see the observation. Right, so now if you look at this particular, let's draw some conclusion over here. Number one, this is not deadlock, because you still have some events that can occur. As long as there might be some events occurring, it's not deadlock. Similarly, as long as the skip can actually happen, it's not deadlock, right? In the case of refinement, in this case, right? Number one, it's not deadlock. You must make sure you understand why, according to the definition for deadlock. However, number two, that's where the term livelock actually comes from. It's actually a livelock, meaning that the lock itself is actually live, not dead, right? The livelock, because nothing useful is being done. Nothing useful is ever done. Ever done. Especially if you look at this particular trace over here. Let me give you some analogy, which you should be familiar with in programming, right? So let me simply put this one over here. What is this scenario equivalent to? Think about if you simply execute the following code. You simply say while loop, and then I simply put true over here. And then that's it. In this case, you cannot really say your system is being deadlocked, because you're still executing something very busy, right? When you execute this particular block of code, your system is really consuming the computing resources all the time. However, is it really doing something useful? No, it is not, because it's simply just basically busy executing the line of code without doing any actual computation. So that's why it's similar to this scenario over here, right? So that's shocking fact number two. Even though at a concrete level we can see ILN, ILL keep occurring, which doesn't seem to be so bad, but if you think about the corresponding abstract scenario, it's really bad, because it's simply corresponding to a scenario where you simply do nothing useful. You just keep skipping, right? That's really important for you to see. So that's why we said there's two shocking facts about this particular model. Let me summarize, and then we can move on. Number one is about this particular part about being able to preserve the invariants is not very useful, because invariant itself is not complete. Number one. Number two, when we try to look at the new events specifically, because every new event is actually corresponding to some skip over here at the abstract level, we really want to make sure these two events do not really diverge, because if they diverge, they wouldn't allow any occurrence of other old events over here. And if we actually try to correspond this to the abstract counterpart in the state space, in that case, we simply skip all the time. In that case, you can see the system is really doing nothing useful, pretty much like the while loop over here. Right, it's a very quick recap about what we discussed. I think we discussed two shocking facts over here about this model variants over here. Make sure you understand them, and then we're going to talk about how we can prove that the model original model M1 is actually divergence free.